Hey everybody, Mr. Tannen here. Back here with another video on Thursday. This is an asynchronous day for all you Algebra 2 folks out there, so hope everybody's doing alright. I was getting a lot of questions about the non-real complex solutions, I should say. Let me add an S there. And how it came up in that Desmos activity from yesterday. So I want to talk a little bit, but when we first started discussing the fundamental theorem of algebra, well, many of you, like the basic understanding is, if we're just thinking in the realm of real zeros, is that the maximum number of real zeros is equal to the degree, which is true. And then some of you said, well, if it's a odd end behavior, it has to have at least one, because that means the ends go in opposite directions, right? But now, if we are thinking about, if we're starting to incorporate non-real complex solutions, well, actually, all of the missing solutions would have to be non-real complex solutions. So let me show you really quickly here. For instance, this x cubed minus 8, right? That's third degree. If you were to just look at this on the graph, which we will do in a second, you would only see a solution at 2. It just passes through. There's actually no multiplicity. So what that means is that the other two zeros are non-real complex solutions. -1 plus I root 3 and -1 minus I root 3. Let's go to Desmos and take a look at that graph. Oops. It recently closed. This thing's in the way, I think. I wonder if I can move it. Well, let me see here. I'll just do Desmos again here. X cubed minus 8. And exactly what you're going to see is what we had just discussed. Only one solution shows up on the graph. So if you know that it's third degree and only one real solution shows up on the graph, what you know is that the other two solutions have to be non-real complex. So if I go here, this was Adrien Legendre, mathematician whose name was given to Haley. So this first question yesterday was saying, sketch a graph of a polynomial function that meets these three requirements. Leading term is 2x to the fifth. So the reason they're telling us that is because now we know it's fifth degree, and it's positive leading coefficient. So as Haley did here, the end behavior is down to up. Remember, this is my left and right. It may be confusing on the video, but I'm going to skip to the third point. It has a real root at x equals -1/2, which you can see Haley put there passing through the x-axis. And it has two non-real complex roots. So if it's fifth degree and it has two non-real complex roots, what that means is it has to have either 3 real roots, as Haley did here, which is perfectly correct because the other two missing ones for this fifth degree are non-real complex. Or the other possibility is we could have multiplicity, which I believe, let me show some other people who did it that way with multiplicity. Oh, I'm on the wrong slide here. Let me see. Oh, Euclid here did a nice job. So this was Carvella who did this one. Nice work. She got the same end behavior. But you see, because it just touches there, she put the real root at -1/2, but it doesn't pass through. It just touches. So that one actually counts twice. So that's 1, 2, 3 real roots accounted for, because this would be repeated for it to be just touching. And so she also has her two non-real complex roots. She put a little squiggly up here, which is great too, because maybe if it's fifth degree, it means we could have the possibility of double squiggles. So let me take a look here. So I wanted to go back to what was Haley's next slide here for the numbers, the build it. So once again, now this is asking the exact same rules on this next slide, but could you actually build the polynomial? And so what Haley saw is 2x to the fifth. She put an x squared, an x, and an x. So that would be fifth degree. The only thing is, Haley, I'm wondering if we multiply these out, if the leading coefficient would be 4x squared to the fifth. because we have a 2x times a 2x times x. Oh, yeah. But everything else is good, and what the good part is, she knew about the two non-real complex roots. Because look, we've got 1, 2, 3 real roots, so the other two have to be complex. Does she have one at -1/2? Sure does, because this is going by halves. I know that can confuse some people sometimes. Let me drop a nice comment here. Oh, I already dropped one. Nicely done, Haley. Ha ha! All right, let's keep it rolling here, and let's look at some other people because let's see if anybody was able to figure out a way to do it with the. Let me see here. I think this would work because it'd be 2x to the 5th. It has a. This is Michael Atiyah. That's Abdul. Nice work, Abdul. So I want to look at this one because this x squared plus 1 is actually what's giving us the two non-real complex roots. So if I were to come back here to my OneNote, hopefully it works. That's my second time doing the video because thank goodness I had to restart my darn computer. So if this is a factor by the ZPP, I could set it equal to 0 and try to solve. Check out what's going to happen, which is why Abdul knew he could put this and Haley also had it. Well, if I end up solving this, I have to take square roots. I would get x equals positive or negative square root of -1, which is just positive or negative I. So that's actually two non-real complex roots. So basically, whenever we see zeros that aren't showing up or are repeated, like for instance, look here, this is a good example. This is another cubic, but you notice it's third degree. But it only really has two roots on the graph, but one is repeated, because at -1, we know this graph would only touch and not pass through. So if a root is repeated, you also count that for as multiple roots. So that's another important thing to look out for. I hope this video helped. Feel free to comment with more questions that come up. And but this idea of non-real complex roots, well, you start to notice anytime you end up with a binomial factor of something like x squared plus any constant, well, when you end up using the ZPP like we just did, well, you'll end up just subtracting and then taking the square root. So you know every time you take the square root of a negative, it's going to have to be plus or minus. Well, we could pull the -1 out. This will be I root 7. Sorry if I went too fast on that simplification, but basically the square root -1 could be pulled out and made into an I. There's also definitely some trinomials for which you would have non-real complex roots, but those are going to be more, you would probably have to find those using the quadratic formula. -b plus or minus the square root of b squared minus 4ac. That's going to be minus 40 all over 2a, which is 2. Check it out. Oh, this is a perfect one. Nice work, Ethan. You really got a good one on this one. Because look, wow, yes. I just pulled this polynomial out of nowhere, and it's going to work out quite nicely because check it out. This is actually going to be 6i because the -1 square root is just I and square root of 36. So it'll be 6i. Don't forget it's still being divided by 2. So this would be -1 plus or minus 3i. So sometimes we could use the quadratic formula to find the non-real complex roots. Sometimes if it's just a binomial like these, you'll see you could just use taking the square root. You could do the quadratic formula, but it's a little bit more work. -b is 0 plus or minus the square root of b squared, which is 0, minus 4ac, which is, oh yeah, this is going to be way more tedious, minus 28 all over 2a, which is 2. So we would eventually get the square root of 7 because we got to factor this. It's basically positive or negative. This would be -1 times 4 times 7. So then we could then take the 4 out, take the I out, but the square root of 4 is 2, so it'll cancel with that. So we'll get the same thing. So you can see when you have a binomial, it's much nicer to do the square root method, but the quadratic formula does work every time. Hopefully this helps for the non-real complex roots. Like I said, drop a comment or a question. Hopefully you take some time to watch it today. Have a great day, everybody.